Welcome to the tutorial series on network analysis made simple. During the previous discussion, we have studied mesh current method, node voltage method, super mesh concept and super node concept of solving the network. During this session, we shall study the network solving using Thevenin's theorem. In a village called Meaux, located 20 miles away from Paris on 30th March 1857, a star twinkled and he was Mr. Leon Charles Thevenin. Friends, do you know? The year 1876, Thevenin graduated and in the same year a telephone was developed by Alexander Graham Bell. As far as the journey of Thevenin is concerned, from 1878 till he retired in 1914, Thevenin served the National Communication Company in France. In 1882, he was shifted to teaching because of his credentials and his apparent interest in teaching. He found novel ways of explaining known results and new techniques as well. In 1883, he described what he thought was his new equivalent circuit, and today it is popularly known as Thevenin's theorem. Friends, Thevenin's theorem basically is a procedure to determine the current flowing through the load branch. And in the process, the entire circuit other than the load branch has to be separated as shown in figure 1. But how do we get such circuits? Here are few examples. Both in figure 2 and 3, you see that the load branch is separated from the rest of the network. In all the network solving using Thevenin's theorem, we have to follow this procedure. Friends, to understand Thevenin's theorem, consider the network shown in figure 1. The network may contain several sources and several linear circuit elements connected in some configuration. The network could also be AC or DC. In such a network, the circuit to the left of the terminals AB can be transformed into a single voltage source network in series with an impedance or resistance as shown in figure 2 using Thevenin's theorem. And this circuit shown in figure 2 is called as Thevenin's equivalent circuit of the given network. The voltage source obtained using Thevenin's theorem is called as Thevenin's voltage source and is denoted by Thevenin. Similarly, the series impedance or resistance obtained using Thevenin's theorem is called as Thevenin's impedance or resistance, as the case may be, depending on whether the network is AC or DC. Now, we can define Thevenin's theorem. Thevenin's theorem states that in any network such as that shown in figure 1 can be transformed into a single voltage source network consisting of Phi Thevenin in series with R Thevenin across the load branch as shown in figure 2. Friends, now let us see how to find Phi Thevenin. Consider the network shown in figure 1, and to find Phi Thevenin, we have to open the load branch as shown in figure 2 and keep all the sources and the remaining circuit as it is, and use suitable circuit solving technique and find the open circuit voltage across the open circuited terminals A and B, let it be VOC, and this open circuit voltage so obtained is called as Thevenin's voltage and it is denoted by Phi Thevenin. Friends, now let us see the procedure to find Thevenin's impedance or resistance. To find R Thevenin, two different procedures are adopted. Procedure 1 is for the networks containing only independent sources, and procedure 2 is for the networks containing only independent sources as well as both independent and dependent sources. So, it is very important to identify the sources present in the network plus More than that, another important aspect is to understand the connectivity of the network. Therefore, if you have doubts in identifying the sources, I suggest you go through my earlier video on voltage and current sources and their handling. If you have doubts in identifying the connectivity of the network, which is very important, I suggest you go through my earlier videos on network terminology, analysis of series and parallel circuits, and star delta conversion. If you have doubts in writing Kirchhoff's voltage equation for the closed mesh or Kirchhoff's current equation for a junction node, I suggest you go through my earlier video on Kirchhoff's laws. Friends, first let us see the procedure 1 to find R-Thevenin for network containing only independent sources and linear circuit elements. Let the given circuit be as shown in figure 1. To find R-Thevenin, first open the load branch as shown in figure 2 and make all the sources present in the network 0. To make independent voltage source 0, short circuit it. To make the independent current source 0, open circuit it. And after this, reduce the network and find the resulting equivalent resistance across the open circuited terminals looking into the circuit as shown in figure. The resulting equivalent resistance is called as R Thevenin. Friends, now let us see procedure 2 to find R Thevenin for network containing both independent and dependent sources and linear circuit elements. Let the given network be as shown in figure 1. As usual, open the load branch as shown in figure 2 and keep all the sources and the remaining circuit as it is and find the open circuit voltage following certain procedure. Next, short circuit the terminals A and B as shown in figure 3. Keep all the sources and the remaining circuit as it is and find the short circuited current ISC. And once you find VOC and ISC, the Thevenin's resistance can be found out by using R Thevenin is equal to VOC upon ISC. Friends, let me summarize the procedure for solving the network using Thevenin's theorem. Step 1, which is very important, visualize the given network, identify the junction nodes, branches, independent loops, and the types of sources. Step 2, if the load branch is not separated from the rest of the network, modify the network. Step 3, keep all the sources and the rest of the circuit to the left of the open circuited terminals as it is and using suitable circuit solving technique find VOC and that VOC is equal to V Thevenin. Step 4. Short circuit the terminals A and B and find the short circuited current ISC using some circuit solving technique. And step 5. Calculate R Thevenin using R Thevenin is equal to VOC upon ISC. Note that here we are following procedure 2 for finding R Thevenin because it is common for any type of network. Step 6. Draw the Thevenin's equivalent circuit as shown in figure 5 and find the load current IL is equal to V Thevenin divided by R Thevenin plus RL. Friends, now let us solve an example to find current in the load resistance RL equal to 3 ohm in the network shown in figure 1 using Thevenin's theorem. First, let us visualize the network. It has 4 junction nodes and they are A, B, C and D. It has 6 branches and they are B1, B2, B3, B4, B5 and B6. The network has 3 independent loops and they are L1, L2 and L3. Also, it has one ideal current source of 2 amperes and one ideal voltage source of 5 volts. Friends, before we go to solve the network using Thevenin's theorem, let me ask you, my first question is, can you solve this network using mesh current method? If yes, how many unknowns are there? My answer is, we can solve it by assuming 3 loop currents and we need to write only two balance equations because we know in one of the branch a source current of 2 ampere is present. Similarly, my next question is, can we solve this network using node voltage method? If yes, how many unknowns are there? My answer is, we can solve it by assuming three node voltages, and we need to write only two balance equations since there is an ideal voltage source in one of the branches. These points you will have to note because you may have to use these aspects in solving the networks. To find phi Thevenin, the load branch is opened as shown in figure 2. Now if you visualize the network, it has only three branches, two independent loops and only two junction nodes. Also observe that 2 ampere current will flow from D to B to C. To find VOC, what strategy should we use? We can use mesh current method by assuming I1 and I2 as shown in figure 3. Note that we know I1 is equal to 2 ampere. We can also use node voltage method by assuming only one unknown V1 as shown in figure 4 because we know the other node voltage of A with respect to reference is plus 5 volts. Friends, we can also use branch current method by assuming branch current I1 as shown in figure 5 and using Kirchhoff's current law we can solve the network. Now, I will decide to solve the network using branch current method and I suggest you solve the network using mesh current method and node voltage method and you see that you must get the same answer. Now, to find VOC or VThevenin, let us decide to use branch current method. Let I1 be the branch current in branch A to C as shown in figure 5. By applying Kirchhoff's current law to junction node C, we get current in branch C to D equal to 2 plus I1 amperes. Now, by writing Kirchhoff's voltage equation for loop 2, tracing it in the direction DCAD, we get 2 plus I1 into 2 plus 4I1 minus 5 is equal to 0. By rearranging and solving it, we get I1 is equal to 1 by 6 amperes. Now, we want VOC, for which we need to write the Kirchhoff's voltage equation for the branch AB in terms of VAB. Hence, writing the Kirchhoff's voltage equation from ABCA, we get VAB minus 2 into 5 plus 4I1 is equal to 0. Substituting it for I1, we get VAB is equal to 2 into 5 minus 4 into 1 by 6. Hence, solving for VAB, we get VAB is equal to 28 by 3 volts. Hence, we know VAB is equal to VOC is equal to VThevenin. Therefore, VThevenin is equal to 28 by 3 volts. Friends, the result obtained for Thevenin is reproduced here for convenience. To find Thevenin, let us use procedure 1 as the network contains only independent sources. Hence, making all sources 0 and drawing the network, we get the circuit shown in figure 6 and we see that 4 ohm and 2 ohm are in parallel and this parallel combination is in series with 5 ohm. Hence, Thevenin is equal to 4 into 2 divided by 4 plus 2 plus 5 which will give us 19 divided by 3 ohm. So, using Thevenin and Thevenin, we can draw the equivalent circuit as shown in figure 7 and calculate the load current IL using Thevenin divided by Thevenin plus RL. Hence, substituting the values, we see that we get IL is equal to 1 ampere. Friends, if you are not sure in network reduction, I suggest you go through my earlier tutorial on analysis of series and parallel circuits. Friends, let us take another example to find Thevenin's equivalent circuit of the network shown in figure 1. By analyzing the circuit, we see that the circuit has three branches, two junction nodes and one closed loop. It also has one open loop since the terminals A and B are open. It has one independent voltage source of 10 volts and one voltage controlled current source of Vx by 4 amperes. To find the open circuit voltage VOC, let us opt for node voltage method and let V1 be the voltage of node 1. Note that V1 is equal to Vx is equal to VOC is equal to V Thevenin. By writing the Kirchhoff's current equation for node 1, we get V1 minus 10 divided by 3 minus Vx by 4 is equal to 0 because current in 2 ohm resistance is 0. By solving for V1, we get V1 is equal to 40 volts and hence V Thevenin is equal to 40 volts. To find ISC, let us short circuit the terminals A and B as shown in figure 3, and this resulted in Vx to become 0 and hence Vx by 4 also is equal to 0. Since the current 0 and the finite voltage imply open circuit and hence we can open the current source as shown in figure 3, and this resulted in a very simple circuit of 10 volts across which 5 ohm is connected and hence ISC is equal to 10 divided by 5 equal to 2 amperes. And we know VOC and ISC and hence R Thevenin is equal to VOC divided by ISC, that is 40 divided by 2 equal to 20 ohm. So using V Thevenin and R Thevenin, the required Thevenin's equivalent circuit is as shown in figure 4. Friends, to emphasize the concept that we have learnt, let's take another very interesting example to find current Ix in the network shown in figure 1 using Thevenin's theorem. The network has three branches and two junction nodes. It has one independent voltage source of 10 volts, one independent current source of 3 amperes, and it also has one current dependent voltage source of 2 Ix volts. To find VOC, we need to open the load branch of resistance 2 ohm as shown in figure 2. Note that it resulted in Ix becoming 0 and also the dependent voltage source voltage 2Ix also has become 0. Now we know that a 0 voltage and a finite current imply short circuit. Hence the current dependent voltage source is shorted as shown in figure 3. Therefore, by writing Kirchhoff's voltage equation for the outer loop, we get VAB minus 10 plus 3 into 1 is equal to 0, from which we get VAB is equal to 7 volts and hence V Thevenin is equal to 7 volts. If you have doubts in understanding these aspects, I suggest you go through my earlier tutorial video on open circuit concept and short circuit concept. Friends, the result obtained for VThevenin is equal to 7 volts is reproduced here. To find ISC, let us short circuit the terminals A and B as shown in figure 4. Now, the network has a dependent source and hence we have to use procedure 2 to find R Thevenin. Let us decide to use branch current method. By applying the Kirchhoff's current law to junction node 1, we see that a current in 1 ohm resistance we get equal to 3 plus Ix amperes. Hence, by writing the Kirchhoff's voltage equation tracing the circuit in the anticlockwise direction, we get 2Ix plus 1 into 3 plus Ix minus 10 is equal to 0, from which we get Ix is equal to 7 by 3 amperes. Hence, ISC is equal to 7 by 3 amperes. Now we know VOC and ISC and hence R Thevenin is equal to VOC upon ISC, and by substituting the values we get R Thevenin is equal to 3 ohm. Now, using Thevenin or R Thevenin, the Thevenin's equivalent circuit drawn is shown in figure 5, and we can find out IL equal to Thevenin divided by R Thevenin plus RL, and by substituting the values we get IL is equal to 1.4 amperes. Friends, is it not interesting? Friends, many issues required to be known while solving the network using Thevenin's theorem are made clear by taking different interesting examples throughout this tutorial. And if you wish to be confident, you should be thorough in basic circuit solving techniques. Number one. And number two, you should be able to visualize the connectivity of the network when certain changes take place, such as opening the load branch, or the sources being short circuited, or sources being open circuited. You should be clearly able to visualize the connectivity and then solve the network. Hope this tutorial has ignited your thoughts, and if so, please forward your feedback and suggestions to my email. Thank you very much for watching this video.